Next speaker is Antonio. He's going to install the microphone. He will come back here. He's going to. So he will give an overview on the thermoelectric materials. So we'll continue the session with him. I don't know if there are questions among our online attendees. Not yet. Okay, so feel free if you want to. So please welcome Antonio Gonçalves from University of Lisbon.
Okay, thank you very much. So I want to thank the organizers to invite me to come here, and I also want to thank Philippe, which is also an organizing to present this very nice presentation on the START project, and that is really related with that I'm going to present. Where is it? Oh, it's here. Okay, thank you. So I'm going to speak about thermoelectric materials. I'm going to give a small overview about thermoelectric materials, and then I'll focus on sustainable thermoelectric materials. This is what we want. So we want basically something that must be used in the future without destroying our society. So the scope of my talk will be on the problem of sustainability. So I'll give a small introduction to thermoelectric materials, really small because everybody knows about thermoelectric materials. And then I'll speak about from classical to sustainable systems. And to do that, I divided this talk in 4 sections. So the first one will be on the introduction to the subject and introduction to sustainability. Then I speak about the classical thermoelectric materials. Then I go behind the classics, in particular with the fine glass electron crystal concept that was really something that made the change. And finally, we will reach the sustainable thermoelectric materials. So, what about sustainability? What about introduction? So, what we want, all us, for everything, what we want is to have a sustainable development. So, and for that, there are 3 main areas, which is the economy, which is the environment, and the society. Actually, the environment is the basis of everything. So we don't want to destroy our environment. So we want to keep it. But we want to have economical growth to develop and give better conditions to the society. And this is quite hard, okay? So because if you want to, increase very much the growth of economy, sometimes it collides with environment systems, with the environment, you destroy the environment. So we must be careful on these 3 areas if you want to have a sustainable development. And what about thermoelectrics? What can thermoelectrics give to that? Is it possible to connect thermoelectrics to this sustainable development? Yes, in principle, yes, because if you look, one of the big problems of our development, of our society is energy. You can feel it now, okay? So actually, most of the energy produced is still from fossil sources. So something like 80%. So we have a problem of energy. And in fact, most of the energy produced are just throw it away as waste heat. So thermoelectrics can help with this because we can use thermoelectric generators. Of course, thermoelectricity can be used for cooling, for other things, but we can use thermoelectric generators to directly transform this waste heat into electricity. So, and they have different or several advantages. They don't make noise, they don't have some movements, they are they can be put in modularity, so they can increase as well as we want to make the investment. So there are a lot of advantages, but there are also big challenges. One is the efficiency, of course. The efficiency is low, typically. But also in the part of the materials, really part of materials, if you forget about the efficiency, which is low, as I said, the materials must be efficient, cheap, and non-toxic. So this is the problem. Okay? So let's look a little bit deeper to the waste heat. If you look to that, you can see that there are different types of waste heat depending on the temperature. So most of the waste heat is for it's low temperatures. Okay, something like between 45 and 50% of the waste heat is going up to 300 Celsius. Okay, basically it's chemical industries. I don't know, at houses, in even cement industry has a lot of heat losses at that region, but also a little bit higher. And the second one, at temperatures above 500 Celsius, are above 500 Celsius, so around 30 to 35% of waste heat, and you can see all the metallurgies are there. Okay, so if you really want to profit from that, the ideal is to profit from all of them. Okay, but it's necessary to have different type of materials. So in our case, we have concentrate more to low temperature materials and low temperature, which means up to 200, 300 Celsius waste heat losses. So, concerning the potential of thermoelectricity for sustainability, as I said, so something like 60% of the energy produced is wasted as waste heat, and these give something like around 100 terawatt hour per year of losses. So it's huge. Okay, so if you really think that it will be possible to profit something from that, even 1% or 2%, it's a lot. It really signifies something, okay? And in fact, what we have now is figures of merit quite reasonable, I'd say. So for these sustainable materials, we have ZTs above 1, which, as you will see, even for classic materials, is what you usually get. So we have, in terms of sustainability, we have the industrial waste heat recovery. So we have several industries that that have a lot of losses, but also the automotive and transport facilities. They have a lot of waste heat losses. In particular, the internal combustion vehicles, which are still a lot of vehicles that we have. Okay, forget Europe. Europe is a good example, I would say. Norway is a very good example in terms of electric cars. But if you go all around in all world, we still have a lot of internal combustion vehicles. And these have a loss of 65% of energy. But also remote and off-grid power. So don't forget that something like almost 1,000 million people are people that lack reliable electricity access. Okay, so and here also thermoelectricity can give some help. And then the new applications like wearable Internet of Things. So these kinds of applications are quite interesting because we can avoid or partially or in a great quantity, we can avoid batteries. Okay? And this signifies billions of batteries. But not only batteries, but also wires. So there's a lot of place, there's a big space to be used there for thermoelectricity. if we found the proper thermoelectric materials and the proper thermoelectric systems. Okay, so let's look to the thermoelectric model market and the evolution of thermoelectric model market. You can see that there is still the big part are cooling at the moment. Okay, cooling is still dominate the thermoelectric models market, and this is okay because it was really very used for medical applications, for cooling of electronic devices, and this is still being a big part. So this is decreasing in percentage, but it's not decreasing in absolute values, because the model market is increasing really fast. But what we can see is really the power generation is really fast in growing. In particular, because of also Internet of Things and wearable things. Well, not so much, but in particular, Internet of Things. Okay? So it looks that thermoelectricity has a role, or can have a role. But as you know, we have problems in terms of thermoelectric materials, in terms of thermoelectric devices, because the thermoelectric materials are challenging to develop, because there is some inverse correlations between Seebeck coefficient, electrical conductivity, between electrical conductivity and low thermal conductivity, and between high Seebeck and low lattice thermal conductivity. So to play with all this almost not so, well, they play against the others, basically. So to have it really working properly is not easy. But even so, it's possible to develop some materials that are good thermoelectric materials. And this led us to the classical thermoelectric materials, which were developed until the 60s. So there was a lot of work in the 50s and the early 60s by many groups, and actually from America, from Russia, from Australia. And this allows the development of relatively good thermoelectric materials by using different strategies. For instance, by optimizing the carrier concentration and to the optimum volume, so something like around 10 to 19 cubic centimeters, that really maximizes the power factor. And for these, it was possible to identify the lead telluride, bismuth telluride as a good thermoelectric materials. Then also playing with the band gap, because all these materials are semiconductors, and optimizing this band gap. So it was possible also to maximize the power factor and to avoid the bipolar conduction. So in this case, also bismuth telluride, lead telluride, but also silicon germanium alloys were identified. Multi-valley band structure, so which increases the effective mass, so increases the Seebeck coefficient. And this was basically, in particular, the lead telluride was what was identified. Then also the high mean atomic weight that reduces the thermal conductivity, and lead telluride and bismuth telluride are good examples. And finally, alloy disorder, which in all of these three types of materials, bismuth telluride, lead telluride, and silicon germanium alloys, were identified. And this mass fluctuation makes the phonon scattering and decreases the lattice contribution to the thermal conductivity. So we have, basically, these were the best materials identified until the 60s. And in fact, they were quite interesting and quite good, because they cover more or less all the temperature range that where we have waste heat. Okay, for low temperatures, from room temperature around up to 200, 300 Celsius, we have bismuth telluride. Then at medium temperatures, we have lead telluride and solid solutions. And finally, for high temperatures, we had the silicon germanium alloys. Okay. So this is what we had. Concerning now looking a little bit deeper to each one, So the bismuth telluride has a good carrier concentration, as I said, has an optimum band gap, which was possible to tune by changing the composition. The structure is, so it has a high mean atomic weight, which decreases the lattice contribution to thermal conductivity and does not affect so much the mobility. So it was good in this sense. And it was, but it has a structure which is a layered rhombohedral structure. It is a van der Waals compound, which means that they are composed by layers. And these layers are, within each layer, are strongly connected, but between the layers, the connections, the chemical connections are not very strong, are quite weak. And basically, mechanically is not really the best, okay, because of this. So good band gap, high carrier mobility, and one thing which is very important, it's by tuning, by changing composition, by doping, we can have N and P. So we can have both types of semiconductors, which, as you know, for devices are really an issue. So we need to have both if you don't want to develop single-layered devices. Okay, so we can reduce the lattice contribution thermal conductivity. So they are quite good for Peltier coolers, but also for low to medium temperature range waste heat recovers. But there are key limitations. Okay, one is the mechanical properties, as I said before, because the structure is quite anisotropic, and in that plane is really brittle, and it has a lot of tellurium. And that, of course, now it is not a big problem because tellurium is not used, so it's just a waste of copper industry. But for a broader use of these kind of materials, it's a problem because it does not exist, point, okay? So, lead telluride. So as I said, it's a multi-valley, has a multi-valley band structure, is also a semiconductor, and it changes with temperature. So it remains close to the optimum band gap when you change the temperature. And we can have alloy, so we can put alloy between lead telluride and lead selenide, and like that, it's chemically it remains basically the same, but you can decrease quite strongly the thermal conductivity. Has a cubic structure, so this is good in terms of anisotropy. It's the less anisotropic material in the cubic structures are okay. You cannot say that it's isotropic, but it's the less anisotropic that you have. And as key properties, so the best performance is between 700 and 900 Kelvin. So it's for this medium range temperature. It has a good gap and can be N-type or P-type, which is also very good because then in terms of coefficient of thermal expansion, so you are just playing with one material, so it's not so important if you make a device. Cannot be so problematic. So there is these band conversions, and then actually the problem, one of the problems is the thermal conductivity, even after alloying, can be not so small, but by nanostructuring it can be really decreased, and in fact ZTs higher than 2 were obtained. I have doubts that we can keep it for a long time. That's another problem, but okay, for publishing an article, it's okay. Okay, there is again a critical limitation of tellurium and a critical limitation of lead, because as you know, in Europe, lead is considered highly toxic, and it's banned from many applications. Okay. Finally, silicon germanium. This is for you. Okay, silicon germanium, they are really very good for high performance. So they can, actually they are alloys, so the alloy disorder makes the scattering and it reduces the thermal conductivity. Actually, if you go if you measure the thermal conductivity as a function of composition, you can see that the minimum thermal conductivity is in the middle, 0.5, 0.5, because of disorder, of course. And it's also, it's for high temperatures. So it was really very, very successful in terms of application, or in a very niche application, which were the radioisotopes thermoelectric generators. This was a big success. So probably you heard about the Voyagers, these spaceships that were sent far, far, far away. And actually, the Voyager 1 is already outside the solar system for a while, and it's still working. So actually, if you want to use some energy sources to send these spaceships outside the sun or far away from the sun, so you cannot use solar energy. So you can use, or the best possibility is to use these radioisotope thermoelectric generators, and they are really very reliable, and they should be really very reliable, because if there is a problem, you cannot go there to solve it, okay? So, and these, in case of Voyager, Cassini, New Horizons, so these are tens of years without any problems and still working, okay? So, so this was based on silicon germanium. Now there are attempts to use other type of materials, not so successful. So I think that NASA is returning again to silicon germanium. And in case of silicon germanium, so the fact of alloying silicon with germanium decreases the thermal conductivity. So there is the operation range at high temperatures. And again, we can, by doping, have a p-type and an n-type semiconductor. The power factor can be very high, and usually it's very high. And the thermal conductivity is low, but not so low. And the main problem is the price. Germanium is an issue, because germanium is very expensive. So I know that there are attempts to decrease the content of germanium in these, keeping the properties. So this could be one possibility for high temperature applications, still, actually. So we have several limitations for the classical thermoelectric materials. One is the toxicity, okay? Lead is toxic, but also tellurium is toxic. Bismuth is not so much, but lead and tellurium are not so good. The scarcity, tellurium is rare. Germanium is also rare, okay? It's not so available. The high cost, so 1 kilogram of bismuth telluride is around $100. But if you go for silicon germanium, it's almost $700 per kilogram. So the price is quite large. And then there is the need of processing, in particular for bismuth telluride. It's necessary to make these or either zone refining to have a strong texture material to have, because of these anisotropic properties, or even single crystal. Actually, the single crystals are the best ones, but are also the most expensive to prepare, and also in terms of mechanical properties are also not exactly the best one, which is related with here. So bismuth telluride, which is the most spread thermoelectric material, classical thermoelectric material, is brittle. And finally, supply chain. So finally, bismuth, tellurium, germanium are classified as critical raw materials by Europe and by United States. Okay, so we have problems, and that's why that was one of the reasons why thermoelectricity did not explode. Okay, price is high. We have all these kind of problems. There are problems on supply chains, and of course, the efficiency is also not so big. But if we can reach a very low price, it's a question of price. So if we got the same kind of properties of these classical thermoelectric materials, but at much lower price, that would be one step to solve it. So we want to go, so we have these old guard thermoelectric materials, and we want to go to the future thermoelectric materials, which means cheap, non-critical materials, scale-up processes, and either maintain or increase the performance of those materials. And in fact, for a while, there was this discovery of these three types of three families of thermoelectric materials: bismuth telluride, lead telluride, and silicon germanium. And for, I don't know, something like more than 30 years, it was kept like that. But in the middle 90s, there was one guy stuck that came with the phonon glass electron crystal concept. And this was really something that changed the things in thermoelectricity. Basically, he came with the idea of having materials that behave for phonons as a glass, but for electrons as a crystal. Okay? So, basically, they tried to find materials where it was possible to decouple electronic and thermal transport, and where some atoms could rattle in cages. Or so there are some strategies like cage filling or complex unit cells or solid solutions. And in fact, this opened the exploration of many, many other type of materials. And in fact, many materials were discovered after that. Okay? And also the nanostructuring came into the room, because many new technologies, many new technology advances in these nanosystems appear in the 90s. Moreover, after there was the idea of multiscaling phonon scattering from point effects until grain boundaries, so in order to scatter phonons with different energies. So I'm just going to present here two examples. The example of Tetrahedrites, which are in fact indeed really being trying to develop as devices. So the Tetrahedrite is a cubic structure. It's a cage type structure where you have at the middle a big void. So the empty Tetrahedrite, it's empty. So this void is empty. So basically, Tetrahedrite is also a mineral. So this is the empty one. So it's cobalt antimony 3. But this void can be filled. And like that, you can reach a composition of air M4X12. And this atom, which is in the void, is not strongly connected to the other atoms. And that allows to rattle inside that box. Okay? And with that, it was possible to reach quite good figures of merit, something like ZT is around or higher than 1.5. But there are several limitations of this. One is it relies on antimony. So antimony is not so bad as fluorine, of course, but it's not exactly the best in the world. And actually, the best rattler atoms are rare earths. That's a problem. Okay. I know that there are some reasonable examples where the rattler are calcium, for instance, but the best ones are with the rare earths. Okay, the second family that I want to speak is Half-Heusler. These are basically intermetallics, where are also cubic and are based in two sodium chloride structure, one inside the other, where one of the structures, just half of the atoms are occupied, half of the positions are occupied. And that opens a gap, and even if you think that it's an intermetallic, it's a semiconductor. So vacancies in one sublattice open a band gap, so it becomes a semiconductor. And this has a quite high effective mass, so which means it has a quite large Seebeck coefficient, and the best results are also with figure of merit higher than 1.5. The power factor is quite reasonable. The thermal conductivity is not so big, but we can decrease it by nanostructuring. And again, I have some doubts that we can keep for a long time this nanostructure. So it is basically for mid to high temperatures range in terms of application. So this could be, it's promising for replacing the lead telluride. Okay? So, but we want more than that. So actually, we want really going to something that is a viable thermoelectric, which means a high ZT, but also earth abundant, based on earth abundant elements and non-toxic and stable. Okay, this is what we want. If we want really to go to sustainability, we need to go to that, and moreover, something that can be recyclable. Okay, and this, what we want is to, of course, we can continue using the strategies that were used to develop all this kind of classical and new type of materials, like for instance, the all dimension strategy, but shift the chemistry to really spread elements like sulfides and silicides, and for sure avoiding rare elements or elements that don't exist so much. So what we want, if you want to go to a sustainable thermoelectric material, so we want to have a high ZT to be competitive with the existing material. So we want to have these materials based on earth abundant elements with at least 100 ppm. Well, it's a limit, it's a number. Non-toxic, so we don't want to have it based on lead or mercury or cadmium or something like that. So elements that are really not so good in terms of toxicity. Low cost, so raw material is affordable for industrial scale. And of course, the process of preparing should not be too much complicated. So quite simple in order to be scalable. And of course, the materials should be stable. Okay, you cannot just use it once or half a year and then it's dead. Okay, so this is what you really want. And let's start. Start from the elemental abundance. Start considering as a reference silicium. So silicium exists all around. There are a lot of silicates, quartz, whatever. Okay, it's really abundant. It's not so abundant as oxygen, but it's really abundant. So let's take it as a reference, and let's look to other elements that can also be, in principle, used for thermoelectricity. Let's look, for instance, for magnesium. Looks fine. Magnesium is perfect. There's a lot of magnesium in the crust. Okay, but also iron. Even copper and sulfur, they are not so bad. Okay? Of course, if you go to antimony, if you put some antimony there, it should be minority. Because there are not so much antimony in the crust. But avoid bismuth, completely avoid tellurium, and try to avoid, well, you need to avoid lead, because you cannot use, at least in Europe, forget it. Okay? So we have here several elements that can be used. And this led us to what Philippe was presenting and what was the subject of this START project, tetrahedrites. If you look to tetrahedrites, basically it's mainly copper, sulfur, which, as I showed before, are quite spread. They exist. They are not so rare. Okay, and then a little bit of antimony. So one part in 7. So it's not so bad. And in fact, it's all around us, as Philippe showed. So It's not a problem for any part of the world. So it's really spread in all world. Okay, so it's earth abundant and mineral is a mineral. Okay, of course the mineral, as also Philippe showed, is not the best one. So it's necessary then to compensate and to play with the synthetic mixture with synthetic tetrahedrites to get the proper properties. But even so, it's a good possibility. So it's a cubic structure, which means that it's good in terms of anisotropy, and has several cubic sides or 2 cubic sides, and these antimony sulfur pyramids. And basically, it is like in the SLAC proposal of Phonon glass electron crystal. So in fact, we have a copper that rattles there. It's not very strongly connected to the other atoms. These atoms that are located in a planar trigonal place, and they scatter quite strongly the phonons, and moreover they are lone pairs that also plays a role in scattering of phonons, which means that it can really have a very low thermal conductivity. So this is one of the main advantages of tetrahedrites, is really the low thermal conductivity that it's observed in this material. And then, of course, we can play with composition, because this is the original one, the original composition, copper 12, antimony 4, sulfur 13. But we can play a lot, in particular in the copper, but also in antimony and in sulfur, substituting one transition elements per another, so copper for another transition element. So it's possible to tune the properties, to optimize the properties in order to get better figures of merit. And in fact, as it was showed, figures of merit around 1 are possible to get. Okay. So this is basically what I've said. So it's possible to substitute and to get proper figures of merit, even if the mineral can have a low figure of merit. So tetrahedrite seems to be one possibility. But there are other possibilities. And as I said, magnesium is also spread. So it exists a lot of magnesium. So, we can look to some of the actual, I'm just going to look to 2 families. So I'm not going to look to the magnesium antimonide. I'm just going to look to the magnesium silver antimony, which in terms of price, of course, you can see that it's not exactly the best in the world. Okay? And there are other problems that it presents, but even so, it's interesting to see and to check what are the properties of this material. And then magnesium silicide, or based on magnesium silicide, so with solid solutions, in particular with tin or with bismuth also. So let's look to the alpha magnesium silver antimony. So it's a p-type. So one is p-type, the other is n-type. So it has a complex ternary tetragonal structure, has a high Seebeck coefficient. However, it's quite sensitive to the synthesis. It can be prepared by different ways. So we basically have used the ball milling and electron assisted, some kind of SPS. So they had quite reasonable ZTs. But we also developed a method to avoid the ball milling just by induction melting and then by hot press, normal hot press. So it's one possibility. And then going to magnesium silicide, it has an antifluoride structure, can be also used as a solid solution. Actually, it's necessary to use in order to tune the band gap. It has a quite good power factor, And it was possible to achieve with optimization ZT is higher than 1.2, so this close to room temperature. Okay. So, looking deeper to magnesium, silver, antimony, it's not so easy to work with this material because it has a quite complex chemistry. The phase diagram is not so clean. There are several impurities that can appear and usually appear in your material. And even the 111 compound, it has several phase transitions depending on the temperature. So you have what we want, the best phase for thermoelectricity is the alpha phase. But we have one phase transition at 290 Celsius to the beta phase, which is metallic, and then at 360, you got the gamma phase, which is very stable. So it's usually hard to get rid of it when it is formed. So the stoichiometry control is really essential, in particular playing between magnesium and silver is really important to get the proper material for thermoelectricities. This is actually not exactly the best composition. This is silver 0.97 and this antimony 0.99 something, okay? Which is, so it is a little bit less than one silver there. And actually, there is a narrow zone where it is possible to prepare the proper in the phase diagram, internal phase diagram, where it is possible to prepare the proper samples. Okay, now going again deeper for the magnesium silicide, so we can tune the band gap by playing with the ratio between silicon and tin. So it is possible to tune the band gap between 0.35 and 0.7, which is quite large. So it's quite good. So it's possible to have large Seebeck coefficients, and actually in our case we got the record of the record is higher than that, so it's higher than 48 microwatts in this temperature range, so at low temperature. So it's really possible to get proper power factors. And so that's it. So these, I think, that are really something in terms of sustainable materials, in terms of future. So the tetrahedrites, which are P-type materials, there was a big effort trying to get N-type, but it was not really successful. So it's a P-type material. The magnesium, silver, antimonide is also a P-type material, and but the magnesium silicide is an N-type material. So we can play between them to get proper devices, but we have problems in terms of these magnesium-based materials. So we have the problem of volatility of magnesium. Actually, magnesium is quite reactive, and not only evaporates and sublimates very easily, but also reacts very easily. There is, in case of magnesium silicide, if you came just from melting, you can have the phase separation. In case of magnesium, silver, and antimonide, you have this problem of several phase transitions depending on the temperature. And of course, magnesium, as I said, reacts very much with everything, in particular with oxygen. So it's necessary to make the synthesis in an inert atmosphere, in particular if you use ball milling. And because of its reactivity, it's not easy to find the proper contact or diffusion barriers or contacts with this kind of materials. And not only the electrical conducting contacts, but also the thermal contacts. So there are still some challenges, in particular for developing devices or devices that will survive for long periods. So finally, we think that sustainable thermoelectrics is viable. So if you look, for instance, the price of the raw materials for tetrahedrites are are less than $10 per kilogram, which is really very cheap. If you compare with the bismuth telluride, or if you compare, of course, don't compare it with silicon germanium because it's really very expensive. So we have, in case of tetrahedrites, ultra low thermal conductivity. In case of magnesium-based materials, it's possible to get high power factors, and the band gaps can be optimized. Of course, we have this sensitivity to the stoichiometry, but it's possible to control these by playing between the ratio between magnesium and silver. So to finish, future directions and research outlook. So I think that we still need to play a little bit more on the materials itself, in particular if you change the way of preparing. But it's also possible to get better properties of nanostructuring. Don't forget that here we are dealing with materials that will work at not so high temperatures. Okay, so it is possible that we could keep the nanostructuring if you play it well, because we don't have so much diffusion at the working temperatures. But in terms of technology, there's a lot of challenges. A lot of challenges in terms of model integration, in terms of contact solutions, in terms of long-term stability, and in terms of scale-up and cost. So this is something that I think that if you really want to develop systems that would be useful in terms of sustainable thermoelectric devices for future, the technology part is really an issue. And with that, I finish, and I thank you for your attention. Thank you very much.
Thank you very much, Antonio, for the very interesting talk. I don't know if there are questions among the audience here. Yes, please.
Thank you very much, Antonio, for a nice overview on the thermoelectrics in general. I have a question regarding, let's say, future manufacturing of the materials, let's say, based on this sustainable part that you have shown, because I recently also purchased something from Technology, and their materials are still based on bismuth telluride. So do you know if there is like an option for the future that they will make something based on sustainable things like you have shown, or what is the problem, why they don't produce already these things?
Well, as I said, the main problem of this kind of materials is that it's basically not really the development of materials, but the development of technology. So you have the tetrahedrite, you have sulfur. Sulfur is very reactive. It evaporates and sublimates very easily, as in the case of magnesium. So I think that we can work with this kind of materials based on magnesium. Probably Cornelius can say more than me on this, but up to 200 Celsius. More than that, I think that probably it will be difficult to avoid some kind of reaction, because they are very reactive, they are very volatile, and for long-term applications, it will be a problem. But I think that basically is a problem of technology. So we have already tested a lot of diffusion barriers, contacts, and we have some ideas, but reproducibility is not so big. Sometimes we got something which is okay, but now we are trying to develop this reproducibility. But these are issues. These are really important issues because the contact resistance, for instance, is critical. You can have a ZT of 10, but if you have a bad contact resistance, the device is dead. Okay? So I think it's more the technological part that still avoids the use of this kind of materials.
Okay, thank you. Any other questions? Or maybe from our online participants? Bruno, do you have any questions? No?
Even online.
Okay, maybe for the next. Okay, so thank you very much, Antonio, for your very interesting talk. Now.